So to finish this section on plate tectonics and how it impacts on global environmental change, I've picked 4 topics to look at in a little bit more detail. We're going to look firstly at how tectonically driven mountain uplift impacts on environmental change on a regional to continental scale. And then in more general terms, we're going to consider how impacts on tectonics related to eustatic sea level change, ocean circulation, and volcanic activity all are potential drivers of environmental change. I put this image in really just because it's absolutely spectacular. What of course you have here is the Indian plate sutured against the Eurasian plate in the form of the Himalayan mountains, and beyond it northwards the Tibetan plateau with India down in the south of the image. A couple of key things then is the scale of this in terms of the area that's covered, as you can see here, and also the average height over this area of around 5 kilometers. And some of the key principles then are actually illustrated by the Himalayan Tibetan plateau. For example, if you have a series of mountains, you have a fundamental barrier to atmospheric circulation. You see in the previous image, for example, the presence of snow in the Himalayan mountains and the impact that will have on the albedo of the area. You'll also generate changes with altitude in vegetation, so as the Himalayas grew over time, the standing vegetation on them would have altered, and that of course in turn then would have impacted on something such as albedo values. Once you establish perennial snow cover, again there's the impact on albedo. The presence of the mountains is going to control distribution of moisture, which again will be another variable superimposed upon changes in the vegetation that are derived purely as a result of altitude. One of the key features about the presence of moisture is very often the existence of localized rain shadows. So for example, in this scenario here, which is equivalent or analogous to the modern Andes, where the prevailing wind direction is from the west to the east and the mountains are on the western side of the landmass, a lot of precipitation will happen in coastal areas indicated here, and a rain shadow will occur to the east of that. On the other hand, of course, if the mountain range is actually on the coastline on the eastern side of the landmass, then the moisture-laden winds can actually pass into the continental interior and potentially precipitation will fall there in that scenario. So the adiabatic cooling over mountain ranges will change the pattern of precipitation, most obviously through the formation of rain shadows. A key variable as well that we'll see associated with the development of mountains is alterations over time in rates of erosion and weathering and sediment flux to different depositional settings. So when we're thinking about the relationship between plate tectonics and how they may impact on changes in eustatic sea level, in other words global mean sea level, there are 2 variables to consider. The first is the total length of mid-ocean ridges that's active across the surface of the Earth, and the second is the rate at which these mid-ocean ridges are generating spreading crust. The faster the rate at which new oceanic lithosphere is being created, the more hot ocean crust there is at any given time. So the 2 variables interact in that when the length of the mid-ocean ridges is greater and the rate of seafloor spreading is greater, you will have greater quantities of this young, hot, buoyant crust. And of course, if the rate of seafloor spreading is faster, that crust is going to be carried further laterally before it cools. Now the net effect of the creation of all that young, hot, buoyant crust is that you're going to uplift the ocean floor. And as a result of that then, the volume of the ocean basins is actually going to become less. You've got the same quantity of water, however, in the oceans, but less volume in which to store it. So the inevitable effect is that you're going to displace that ocean. It's going to rise at the margins of the continents, and you're going to generate transgression. We're going to look at a case study in Cretaceous epicontinental seas. And of course, when we were looking at chalk and the formation of that, this was one of the examples we used. Now, the Cretaceous as a time is characterized by high sea levels. We also have ice-free poles, so we've no way in which we can lock water away at that particular mechanism. And we also have high spreading rates in the world's oceans after the destruction of Pangaea and the continued establishment of the formation of the Atlantic, for example. As a result of those sorts of variables, we have sea levels that are around or so 100 meters higher than they are actually today. So you get widespread development of these shallow epicontinental seas. You can see here the distribution of it across North America. North Africa is similarly affected, for example. Most of Western Europe is accumulating chalk at this time in these shallow marine environments. Changes in the plate tectonic configuration across the surface of the globe have significant implications for the existence of ocean gateways and conduits by which we can circulate water across the surface of the globe. It's important to remember that these alteration to the structure of the ocean basins won't just impact at surface levels on the currents that are driven by winds. It'll also impact on deeper ocean circulation, which is driven by density differences in the water masses. Now, oceans, of course, make a major contribution to heat transport away from low latitudes at the equator towards the poles. But changes in structure of ocean basins are also relevant to things such as how you have atmospheric teleconnections between low latitudes in the tropics and high latitudes in the polar regions. And also, you're going to influence the distribution on a seasonal basis of sea ice, and of course that has significant implications for variables such as albedo. One of the interesting phenomena that could occur should we get ocean circulation that facilitates the introduction of warmer waters at depth and leads to deep sea warming is we may make clathrates unstable. Now, clathrates are frozen methane hydrates that exist a few meters, a short distance below the top of the sediment column in the world's oceans. And it's speculated that the warming at depth of the oceans, for example, by a changing distribution of ocean currents, could result in the release of such methane. Now, methane, of course, itself is important as a greenhouse gas, but over time and relatively rapidly it oxidizes to CO2, which stays even longer in the atmosphere. So we could have a potential positive feedback mechanism if these clathrates become unstable. Now, it's actually very difficult in a deep time scenario to reconstruct ocean gateways and how environmental conditions might have changed in response to changing the pattern of ocean gateways over the surface of the Earth, because all the oceanic crust is less than 200 million years old, and thus the proxies that we would use, the bits of information that we would use for reconstructing climate, such as the types of sediment are present or the types of fossil that are present, are not available. We've already looked at how volcanism can modify global environmental conditions whenever we looked at outgassing of, for example, sulfur dioxide or carbon dioxide from volcanoes. And of course, plate boundaries are a major area on the globe in which we get volcanic activity. What I want to look at here is the phenomenon of large igneous provinces. These are huge in their scale, and their emplacement is associated with continental rifting. And the example I want to draw your attention to here is the Central Atlantic Magmatic Province, which is associated with the opening of the Atlantic Ocean following the breakup of the supercontinent Pangaea. As you can see, today relics of this Central Atlantic magmatic province can be found in Western Africa, in the northern part of South America, but at the time of their formation they essentially formed one contiguous mass on an absolutely huge scale. Just a reminder that we're talking about the end Triassic and the start of the Jurassic periods here, so around about 200 or so million years, and the event and the emplacement of the Central Atlantic magmatic province is associated with the rifting of Pangaea and a major episode of sea level rise eustatically. We also have, at this particular time, one of the major mass extinction events that punctuate the geological record. And the interesting aspect to do with this end Triassic mass extinction event is that its association with the Central Atlantic magmatic province, a major igneous province, is a phenomenon that's also associated with the end Cretaceous, shown here as a K, mass extinction event, and the end Permian mass extinction event as well. So here's the large igneous province known as the Central Atlantic magmatic province. You can see that in terms of its area, it had originally been something equivalent to about the size of South America today. There's an idea of how much basalt magma was erupted in, amazingly, less than 1 million years. Interestingly enough, the actual deposits straddle the equator, which of course, as we've seen before in the course, there's very, very significant rates of weathering associated with the production of things such as bauxites, laterites, for example. So very distinctive weathering regimes associated with equatorial latitudes today, and presumably also equatorial paleolatitudes, and we'll come back to that shortly. So if we think about this million years or so during which we're emplacing the Central Atlantic magmatic province, we of course are going to have the same phenomena that we've encountered before on smaller scale with individual volcanoes and their eruptions. We're going to have a lot of emissions, most notably key things such as sulfur dioxide, which would have served to reduce the incoming solar radiation and induce short-term global cooling. Carbon dioxide emission may have had the opposite effect in terms of actually facilitated on a longer term global warming, and it's also possible that we would have had catastrophic destabilization of methane hydrates with the eruption of these large volumes of igneous rocks into marine settings. We should also think longer term after the emplacement of this major igneous province. Effectively what you've done is you've taken the pre-existing landscape and you've submerged it below this very distinctive lithology, and in all probability that very distinctive lithology is going to have its own very distinctive weathering pattern. And there are some suggestions that perturbations that you get in terms of ocean geochemistry in the sediments deposited in the oceans at this time are linked to changes in the weathering patterns, for example, that were happening on land. And it may be critical in this particular case that it's at an equatorial paleolatitude with its own very distinctive and accelerated rates of weathering. Of course, if we're going to start to weather these basalts, high rates of silicate rock weathering are a mechanism by which, on a geological timescale, we could actually draw down atmospheric CO2 and induce global cooling for a sustained period of time. And of course, that mechanism in its simplest case can be represented by the Urey reaction, where we have our carbon dioxide sourced from the atmosphere, we have our silicate rocks in the form of these igneous basalt eruptive rocks, and through the geological cycle in the formation of carbonates, we end up actually locking away that CO2 for sustained intervals of geological time.